Hi, my name is Kaden Shannon, and I recently flew my Phoenix 1 rocket for the last time recently. Instead of using fins like a normal model rocket that you'd get at your local hobby shop, Phoenix 1 uses thrust vector control. Don't worry, if you don't know what that is, I'll explain it more in this video. Before we get to the launches, I think it's important to talk about how I even got to this point in the first place. So, it's 2020, and I'm watching YouTube, and I stumble across a channel called BPS.space ran by Joe Barnard. And whenever I saw his videos where he was launching thrust vector control model rockets, I thought that was the coolest thing in the world. And I thought to myself, maybe I should try that for myself. Now, hang on a minute. I've never done any engineering, programming, electronics, or anything of that sort before this. Where do you even start if you want to do something like this? So, I figured my best course of action would be to take small steps towards doing a complicated project like building a thrust vectoring rocket. At the start of 2021, I took Mark Erber's creative engineering course where I learned the basics of Arduino, electronics, and engineering. Shortly after that, I built my first model rocket. It was a small kit from a company called Estes. This just had 3 fins and an 18mm motor. And here's how the launches went.
You got it! Well, parachute!
Yikes. That was not good. So I bought another one, and I tried again, and this one went a lot better. So now that I knew the bare basics of model rocketry, I decided to take the leap and try building my own rocket from scratch for the first time. Admittedly, the rocket I decided to build was extremely ambitious for my first rocket ever. It stood at a height of 63 centimeters, had 3 E16 motors, and the most important parts of the rocket, the motor mount and the fins, were both 3D printed out of carbon fiber, and I called this Serpent 1. After God knows how long of delays due to redesigning it, parts getting damaged, and stuff like that, I finally launched it on February 16th, 2022. This flight went perfectly. It flew to an altitude of about 433 meters, which is about 1,420 feet, before deploying its parachutes. The only thing that wasn't planned for was it drifted a mile downrange, but that's a story for another day. With all this experience, I decided that I was finally ready to start working on a thrust vector control model rocket. At the start of 2023, I started working on Phoenix 1, but that raises an important question. How does a thrust vector control model rocket work anyway? Before we start talking about thrust vectoring, why do model rockets even use fins in the first place? For a rocket using a passive control method to remain stable, it must have its center of gravity above its center of pressure. If they're too close together, or if they're flipped the other way, the rocket will be unstable like this. The center of gravity is the point where the weight is balanced on each side, or also you can think of it as where you can balance it on one finger. The center of pressure is like that, but with aerodynamic forces. It's where the aerodynamic forces are equal on each side. An easy way to visualize this is by taking a cutout of your rocket and then balancing it. I learned this while I was at Space Camp in Huntsville, and it helped me visualize it a little bit better. A more intuitive way to visualize it, at least for me, is that if you look at a rocket from head on and you rotate it a little bit, you can see how more of the fin is exposed, so that would be pushed down by the airstream. Next, I asked the question, what is thrust vectoring and why does it work anyway? So I have a model here that shows a rocket with an engine pointing straight up through the body. When this engine is lit, it produces a thrust of 15 newtons, which is represented by this vector. So what would happen if I changed the angle that the engine is pointing? So let's rotate it 5 degrees. Now that the thrust vector is pointing in a different way, why does it matter? So if I draw a straight line from the center of gravity to the center of the engine, we get a right triangle. The hypotenuse is 15 newtons and the angle is 5 degrees, so we can use trigonometry to find the legs of the triangle, which represent the force vertically and horizontally. So to find the force pointing up, we can use cosine of 5 equals x over 15, which is about 14.94 newtons. Then we can find the horizontal force using sine of 5, which is equal to y over 15, which is about 1.31 newtons. If I push the bottom of this marker to the side, it creates a force around where I'm holding it called a torque. If I know how much force I'm pushing it to the side with, the angle between my finger and how I'm pushing it to the side, and also the distance between where I'm holding it and the bottom, we can calculate it. So let's bring that back to our rocket model. Thinking back to the marker, the distance between where I was pushing it from and where I was holding it from is the rocket's center of gravity to the center of thrust, which is the middle of the motor. This is the lever arm or moment arm as it's often referred to. For this model, let's say it's a half meter. The angle between my finger pushing the bottom of the marker and the moment arm would be the 5 degrees that the motor is gimbaled. The force that I was pushing the marker to the side with would be the thrust of the motor, which is 15 newtons. Now that we know what all these variables are, we can calculate the torque. The equation to calculate torque is tau equals the lever arm times force times the sine of theta. First, let's multiply the force, 15 newtons, by the sine of 5 degrees. Sine of 5 is roughly equal to 0.0872, so if we multiply that by 15, we get 1.31 newtons. That's the same number we got earlier when we figured out the horizontal force on the rocket. So now tau equals the horizontal force on the rocket, 1.31 newtons, multiplied by our moment arm, 0.5 meters, which is 0.654 newton meters. We can calculate the torque for whatever the angle of the motor is. Now that we know what the torque is, we can find the angular acceleration that the rocket experiences. This is how fast it rotates. We find this by taking the torque and dividing it by the mass moment of inertia. The mass moment of inertia, or MMOI, is a measure of an object's resistance to rotation. For simplicity, let's just say that the MMOI is equal to 0.06 kilogram meters squared. So the angular acceleration the rocket experiences is 0.654 newton meters divided by 0.06 kilogram meters squared, which is equal to 10.9 radian degrees per second, or 624.5 degrees per second squared. This is a simple overview of the dynamics of the rocket, but the important takeaway from this is that a rocket's orientation will change when we change the angle of the motor. If we know how the rocket's orientation changes when we rotate the motor, we can use that to help keep the rocket stable. So now that we know how changing the thrust vector of the rocket affects its orientation, how do we know how to move that motor to keep the rocket stable? Phoenix 1 uses a proportional integral derivative controller, or PID controller. This is a feedback-based controller that adjusts its output based on the error from a set point. For a rocket, we are trying to keep the attitude stable, so the set point and error are measured in degrees. The set point, or the target attitude, of the rocket is 0 degrees, which is straight vertical. Let's say that after a second of flight, the rocket is now tilted over 10 degrees. This will make sense in a moment, but let's define these variables. Kp is equal to 0.5, Ki is equal to 0.2, and Kd is equal to 0.1. So we have an error of 10 degrees, which is E of t. A PID controller is split up into 3 parts. We have a proportional term, an integral term, and a derivative term. Our proportional term is just the error, 10, multiplied by Kp, the proportional gain. So in this case, it would be 0.5 times 10, which is 5 degrees. Next, we have our integral term. For the simplicity of this model, we have a line with a linear growth, so the integral of 10 degrees over 1 second is just 5. So we multiply 10 by Ki, the integral term, which is 0.2, which gives us 1 degree. Finally, we'll solve for the derivative term. The derivative is the change in error over the change in time. Our change in error, or dE, is 10 because 10 minus 0 equals 10. The change in time is 1 second, so 10 divided by 1 equals 0. Then we multiply this by our derivative gain, Kd, which gives us 1 degree. When we add all these together, we get a sum of 7 degrees, which is how far we'd gimbal the motor. Phoenix 1 does this nearly 100 times per second to determine the best orientation for the TVC mount. The gains that a PID controller uses are different for every rocket because of the differing lengths of moment arms and the mass moment of inertia. I added some resources from BPS.space and Hamburg's space mission that explain how to determine these gains in more detail and explain it way better than I could. Now that we understand the theory, let's look at the actual hardware behind the rocket. The most important parts of the rocket are the thrust vector control mount, the pyrotechnic mount, the parachute ejection piston, and the flight computer. In early 2023, I began working on my first thrust vector control mount. You'll find I'm very creative with my naming schemes, and I called this one Thrust Vector Control 1, or just TVC-1. It has 2 SG90 servo motors, which control the mount. There's 3 main parts. You have the outer gimbal, the inner gimbal, and then the motor sleeve. This holds a 29mm rocket engine and fits in a 74mm body tube. In September of 2023, I did a static fire test with this mount to verify that it could handle the forces of the motor and gimbal while it was under thrust, where it passed without an issue. The ejection charge mount is a lot simpler than the TBC mount. This just holds the pyrotechnic charges that deploy the rocket's parachute, and also the U-bolt that the shock cord connects to that runs up to the rocket's nose cone. The parachute ejection piston is pushed out of the rocket whenever the pyrotechnic charge goes off. This pushes the parachute and the nose cone off of the rocket so that way it can softly descend under parachutes. It's needed for this design due to the way the pyrotechnic charge is made. If the parachute were to hit it in the wrong way, it could break it open, causing it to fail. Not that it didn't fail otherwise. The most important part of the entire rocket is the flight computer. This is a BLIP computer that was designed by Joe Barnard for his landing model rocket series, which I linked in the description below. It has 5 extremely important parts: the Teensy 4.0 microcontroller, which is the CPU, the MPU 6050 IMU, which allows it to determine its orientation, the BMP 280, which allows it to determine its altitude, the SD card holder, which allows us to log data, and the 2 servo output pins, which allow us to control our thrust vector control mount. Now that we understand how Phoenix 1 works, let's look at its 7 flight tests. Half a second into the flight, noise from the barometer caused the rocket to think it was descending. The way I originally had the flight software set up was that if the previous altitude was greater than the current altitude, it would turn off thrust vector control and prepare to deploy the parachutes. The noise from the sensor caused it to think it was descending while it was still going up, turning off thrust vector control and ultimately causing the flight to fail. And also the lean you see it take off the pad is due to the battery being strapped to the back of the PCB. And whenever it lifts off, it starts to lean backwards. So after this flight, I designed a new PCB mount and a new battery mount that would put the battery right in the middle of the rocket, and it flew for the first time on flight test 2.
5, 4, 3, 2, 1.
Flight 2 went a lot better than Flight 1, but I made one really dumb error in the flight software. The x-axis servo motor was moving in the wrong direction, so when it started tilting to the right, it started helping to induce the flip rather than counteract it. So that was preventable. I don't know how the flight would have gone if it was the correct way. I don't think the result would have been much different, but just a dumb error that I made, and it was corrected for Flight 3. Flight 3 was the luckiest of the 7 flights. Right after liftoff, it began to point into the wind and started spinning a little bit, helping to stabilize it. And it successfully made it the whole way through its ascent, and then deployed parachutes and softly landed. Right after the flight, I thought it was successful, but once I looked at the TVC data in a bit more detail, it appears that it didn't really do much. It was completely luck-based, and I would find that out the hard way on Flight 4. There's not too much to say about Flight 4. Basically what happened was right after liftoff, the IMU thought that it was pitched over 90 degrees due to a calibration error, and it tried to correct for that, but when you try to pitch 90 degrees horizontally, it'll take it straight into the ground. For Flight 5, I tried adding a second calibration of the IMU into the flight software, hoping that would fix the issue, but I didn't get a chance to test it because about a quarter second into flight, the battery disconnected, causing it to come a little closer to me than I would have liked. It's not as close as it looks in the video, but it was definitely too close for comfort. And now's probably a good time to mention, I have a packet worth of safety procedures that I take with me to every single launch. And if you're going to do anything remotely like this, please have safety procedures. It keeps you safe and it keeps the people around you safe. After spending nearly a month rewriting all of Phoenix 1's flight software, I was finally ready to fly it again at the start of June. Major changes included fixing the PID controller, redoing the math that calculates the rocket's orientation, and reorganizing all the variables so it's easier to debug. And here's how it went.
2, 1. Boys, 1.
This flight marked my first ever successful TVC launch, and I couldn't be happier with how it went. Phoenix 1 remained within 5 degrees of its set point for the entirety of the ascent until motor burnout. Now, right after burnout, you'll see the parachute doesn't deploy, which is not good, and the reason for this is because the battery disconnects from the flight computer. Now, we'll talk about the actual cause for that in a minute. That's just what I thought it was at the time. But luckily, it landed on its side relatively softly, so nothing was damaged, and I could prepare it for Flight 7. Flight 7 was just a repeat of Flight 6, but with one change. A second into flight, it would divert 3 degrees to the right to avoid the launch pad. This is needed for landing rockets, so that way they don't land on the launch pad, and I just wanted to test it out to see how it would go with Phoenix 1 since I knew it was going to work this time. Between these flights, I finally found the source of the issue that had been plaguing all of the launches to this point. Basically, what was happening with the flight computer disconnecting from the battery was the servos would draw too much current from the flight computer, so the voltage would drop, causing the computer to restart. So it was a simple change. I just added 2 capacitors to the back of the servo pins so that way they could draw power from it whenever they demanded more than the computer could supply, and it worked perfectly. So here's how Flight 7 went.
3, 2, 1.
Flight 7 went even more perfectly than Flight 6 did. Instead of 5 degrees, it remained within 3 degrees of its set point for the entire ascent, other than the initial pitch over maneuver where it overcorrected by about 1.5 degrees. Other than that, though, it was a perfect descent, and the parachute actually deployed this time, letting the vehicle softly land. So, once this rocket touched down, it had completed every single goal that I set for the program, and I couldn't be happier with how it went. To look back at the goals I set for Phoenix 1, I wanted to build a thrust vector control model rocket that could control its attitude during ascent and softly land using parachutes. After a successful flight, I wanted to refly it one more time just to verify that it wasn't due to luck, and I also wanted to develop hardware and software that I could use or inspire designs from for later rockets that I build. and I'm glad to say that it was successful in all departments. So, what's next? I've started working on a model rocket that's capable of propulsive landing, which is a very difficult problem to solve. Now, this is still in its very early stages, so I don't have too much to show for it quite yet, but as I finalize more stuff, I'll release information on X and on my website, which are both linked in the description. But on that note, thank you for watching, and thank you to all those who followed along with Phoenix 1, and I'm excited to document my journey into landing model rockets.